welcome back, and in this presentation we will speak about the cracked moment capacity of a reinforced concrete T-beam. And here we have an example, and the aim is to calculate M sub CT of the simply supported T-beam and check if the section is cracked or not. Cracked here just means that the applied moment is greater than the cracked capacity of the section. Alright, what is the formula? M sub CT is equal to stress multiplied by the section modulus, and in this case the flexural tensile stress, which is 0.6 square root F dash C, and we take away the early shrinkage drying tensile stress. The section modulus is the uncracked second moment of area divided by y, and y is obviously the distance between the neutral axis and the extreme tensile face of the concrete beam. Now, where did we get this formula from? M sub CT is equal to stress multiplied by Z. We got it from the flexural formula, and this is why this is the most important formula to always remember. Sigma is equal to my over I. So the question is, when can we use the flexural formula? To what extent can we use it? We can use the flexural formula as long as the beam is linear elastic. So in here, if you remember the moment curvature relationship that we spoke about in the previous topic, the beam is linear elastic in stage 1, stage 2, and even up to stage 3, even up to the yielding moment where steel yields. So we can use it anywhere along this line here. Anything above the yielding moment, so when we calculate mu, we cannot use the flexural formula. So we can use the transformed area method in the elastic section. Once we get to the ultimate moment, we have to use the force equilibrium method. Okay, we have a simply supported beam here. The length here is 6 meters. W star is 10 kilonewton per meter. And M star, which is the applied moment, is WL squared over 8. And that will be 45 kilonewton meters. We go down and we find the T-beam properties over here. I suggest maybe you take a screenshot of this because there's a lot of information here in case you want to revise it. Let's quickly go through it. We have a flange width of 1200 millimeters. The flange thickness is 100 millimeters. The beam width is 150. And then the stem depth is 350. The overall depth is 450. The concrete and steel properties, F-C is given to us as 40 MPa. So we can work out the flexural tensile stress, which is about 3.8 MPa. The shrinkage drying stress is given to us as 0.5 MPa. And the modulus of elasticity of concrete is 32,800 MPa, and steel is 200,000 MPa. The top and bottom cover is 30 millimeters, and top steel is 2N16s, bottom steel is 2N20. The diameter for the stirrup is 10 millimeters. So if we come here, the top and bottom cover, 30 millimeters, is from, let's say the bottom cover is from the bottom of the concrete to the underside of the stirrup. And the top cover is from here, the top face of the concrete, to the stirrup level. Alright, step 1, we calculate the depth of the neutral axis. The formula is the sum of A bar multiplied by Y bar divided by the sum of A bar. The neutral axis depth is always calculated from the compression face of the concrete to 0 strain, as you can see here in the strain diagram. Okay, the first step we do, look, you can take the steel into consideration and you can ignore it. If you ignore the steel, you will be a little bit more conservative. And if you take the steel, obviously it will be more accurate. So to take the steel, we have to transform the steel area into concrete area. Because the beam is considered to be linear elastic. And that's what we do for composite section. If we want to allow a linear elastic behavior for a composite section, you have to have an equivalent area as in one material only. So the first thing we do is calculate the modular ratio, EF divided by EC, and that will be 6.1. 200,000 by 32,800 is 6.1. The equivalent steel area up the top, ASC multiplied by n minus 1, and the bottom steel is AST multiplied by n minus 1. These, we convert the steel area into a concrete area because the stiffness of the steel is so much greater than the concrete. To calculate the neutral axis, the first thing you need to do is choose a datum. You can choose the top or bottom. But why do you think I chose the top? Because if you choose the top, then the answer of the neutral axis will be from the top. The dimension will be from the top. So we calculate the area of the flange first. So the A1 is 1200 by 100. And Y1 is basically the distance between the centroid of the section to the datum that we choose. So for the flange, for example, the centroid of the flange is here somewhere, which half the flange thickness. So that will be 50 millimeters. Okay, and this is symmetrical, by the way, so we don't have to worry about the X bar. We are only calculating Y bar. All right, the top steel, we calculated the area before, which is ASC multiplied by n minus 1. Okay, that's 2050 millimeters squares. And Y2 is the distance between the center of the reinforcement to the datum that we have chosen. So let's say the reinforcement is here. So the center is the distance between the center here and the top. So how do we work this out? Y2, it will simply be 30, which is the cover, the top cover, plus 10, which is the ligature diameter, plus half the bar diameter, 16 divided by 2, which is 48 millimeters. And then the web, the area is 350 multiplied by 150, 52,500. And then Y3 is 350 divided by 2 plus 100. And then the bottom steel, again, very similar to what we did to the top steel. So we take it from the center of the bottom, the center of here, the bottom steel here, right up to the datum that we have chosen. Okay, I'm guessing you guys understand this so far. And then we plug in this formula. dN is the sum of A bar multiplied by Y bar divided by the sum of A bar. So we take all the values that we worked out up here and plug it into the formula. And then we will end up getting the depth of the neutral axis is 122.74 millimeters from the top. Okay, step 2. Calculate the uncracked second moment of area, I gross, using parallel axis theorem. The equation is the sum of big B d cubed divided by 12 plus area times the distance squared. Now little d here represents the distance between the centroid of the section that we are interested in to the neutral axis depth that we have calculated, which is 122.74 millimeters. Okay. Now remember that the bending is around the major axis. So for the flange, for example, let's take the flange. We break all the flange separately to the web and the steel. The flange here, I1, BD cubed over 12 is 1200, and in this case, big D will be the 100 millimeters. Plus the area, which is A1, 1200 times 100, and then little d, which is D1 in this case, will be the distance between the centroid of the flange from here to the neutral axis depth. So that will be 122.74 minus the flange with half of it, which is 100 by 2, and that will be 72.74 millimeters. And if we square that, it will be 5291 millimeters squared. And we do the same for the top steel. Of course, the steel here, we will only look at the area. So the area for the steel is ASC, which is 402 millimeters squared multiplied by n minus 1, which is 6.1 minus 1. And that will be 50 millimeters squared. And in this case, D2 is the distance between the center of the top reinforcement to the neutral axis depth, which in this case is 122.74, minus the cover depth 30, minus the ligature diameter 10, minus the bar diameter divided by 2. That will be 5586 millimeter squares. Almost there. Now we look at the web. The web, the moment of inertia for that is 150, that's B, and D is 350 cubed over 12, 5.36 times 10 to the power 8 millimeters to the power 4, and the area for that is 350 by 150, 52,500 millimeter squares, and the distance is the center, the centroid of this web to the neutral axis depth, which is 100 plus 350 minus, so that's 350 divided by 2, so this will be half of the 350 divided by 2, minus the neutral axis depth. Okay, and if we square that, it will be 23,183 millimeter squares. And the distance between there, the centroid and the neutral axis, is 152.26 millimeters. Finally, the bottom steel, similar to what we did to the top steel. So we have 628 multiplied by n-1, which is 6.1 minus 1, 3202 millimeter squared. And the distance in this case would be from the center of the bar to the neutral axis depth, which is the total depth for the section is 450 minus 122.74, and then we take away the cover minus the, which is 30 millimeters, minus 10, minus the bar diameter divided by 2. And that will give us, and if we all square that, that will give us 76,873 millimeter squares. And of course, the distance between the center of this bottom reinforcement to the neutral axis depth is 277.26 millimeters. Now, finally, we substitute into the formula. And as you can see, it's such a big formula here. But the answer then, I growth is 2.746 multiplied by 10 to the power 9 millimeters to the power 4. Okay, now to step 3. Calculate the cracking moment M sub CT. We've worked out I growth. It's easy now to work out the section modulus. It's I by Y. So we got 2.74 times 10 to the power 9. And we divide that by Y, which is the distance from the neutral axis to the extreme fiber in tension, right at the bottom. So it's 450, which is the full depth minus the neutral axis, and it is 327.26. That's the value for Y. Yet there is a big value for Z, and therefore M sub CT is the flexural tensile stress minus the shrinkage stress times Z. And here we have 27.64 kilonewton meters, and that is the cracking moment. This is the moment that will first crack the beam. Alright, the final step. Previously we worked out the applied moment was 45 kilonewton meters. Cracking moment is 27.64. So therefore, M star is much greater than the cracking moment. The section is cracked by about 39%. Okay, I've created an Excel sheet to make life easy for you guys. You can download it. I'll put it in the description box below. I will show you here how to use it, but before we open it, I'll give you the password. You'll need a password to get in. And the password is Big T Beam Design. So T Beam Design is one word. Okay, here is the little Excel program that I did for you. I followed that same example that we went through in this Excel. So we got 6 meters length, 10 meters, the load. Any shaded area, you fill it in. Okay, so here is the flange width and the thickness and so forth. Okay. And over here we have the steel properties, and with the steel reinforcement you can change this. So for example, we have 2 and 16 as like the example, but if you want to change it to 2 and 20s, all you need to do is type the number of reinforcement you need and just change, say, N16 to 2 and 20, and Excel will automatically extract the first and the last number, and it will calculate the area of steel automatically for you. Okay, let's have a look. I was going to go through the results if we didn't allow for the steel, if we didn't use the transformed area and allow for steel in our calculation. What would the results be? Let's have a look. Let's have a quick look. I was interested to see how much difference it would have made. At the bottom here, you will see the results of the neutral axis depth as well as the section modulus. The final result, the cracked moment, M sub CT, is 27, it should be 27.64. So why has that changed? Oh yes, because I did a 2N20. Now it's actually 2N16. So we'll change this back to 2N16. All right. Let's have a look. Just 27.64. It will be automatically in red because the cracking moment is less than the design moment, and it will tell you by how much. If we don't allow the steel, you can come over here and put 0 to the steel. You can just put this value as 0 and put the values for the bottom steel as 0 as well as the ligatures. Let's see how much difference it has made. The moment now is 24.69. So it's a little bit less. Now it's more like 45%. It's cracked by 45%. So, so if you don't allow the steel, yes, you are more conservative. Okay. So yeah, I hope you enjoyed this. And yeah, if you have any questions, please comment below, and I'm happy to answer it. And if you're finding it hard to open the computation, please let me know. And yeah, please share, like, and subscribe so that others may also learn. And we hope that you have a great afternoon.